Hello everyone, and thank you for joining me. Today we are going to explore a fascinating and clinically vital topic, bilirubin metabolism and biodynamics. Over the next few minutes, we will walk through the biological journey of bilirubin, the precise molecular transporters involved, and the composition of bile. Let's get started. We will begin with part 1, the life cycle of bilirubin. We'll follow its path from the breakdown of red blood cells all the way to its clearance by the liver. To understand bilirubin, we first have to look at its origins. Bilirubin is the central end product of heme metabolism. Every day, the human body produces between 250 to 350 milligrams of it. About 85% of this comes straight from the catabolism of old, worn-out red blood cells, a process handled primarily by macrophages in the spleen and liver. Once formed, this unconjugated bilirubin faces a challenge. It is highly lipid-soluble and water-insoluble. To travel safely through the watery environment of our bloodstream, it needs a carrier. It binds tightly to the protein albumin. This binding is absolutely essential. Without it, free bilirubin can cross cell membranes and cause severe tissue toxicity, most notably brain damage in newborns, a condition known as kernicterus. Once the albumin-bilirubin complex reaches the liver, the real processing begins. The bilirubin detaches from albumin and enters the liver cells, the hepatocytes, through sinusoidal OATP transporters. Inside the cell, bilirubin makes its way to the smooth endoplasmic reticulum. Here, a crucial enzyme called UDP glucuronal transferase, or UGT1A1 for short, gets to work. It attaches glucuronic acid to the bilirubin. This process, called conjugation, transforms the bilirubin from a water-insoluble toxin into a water-soluble compound, ready to be safely flushed out into the biliary system. Now that it is water-soluble, conjugated bilirubin must be actively pumped out of the hepatocyte and into the bile canaliculi. This heavy lifting is done by a transporter known as MRP2. It is important to note that this secretion is the rate-limiting step of the entire hepatic bilirubin metabolism process. If this specific mechanism fails or mutates, it leads to a buildup of conjugated bilirubin in the blood, a classic hallmark of Dubin-Johnson syndrome. To quickly summarize the journey so far: first, catabolism. Heme breaks down in the macrophages. Second, transport. It rides through the blood attached to albumin. Third, conjugation. The liver makes it water-soluble via glucuronidation. And finally, excretion. It is pumped into the bile via MRP2. This brings us to part 2 of our presentation: bile composition and transporters. Now that bilirubin is in the bile, let's look at what else makes up this vital fluid. Bile isn't just a waste receptacle. It's a highly specialized fluid made possible by a specific toolbox of transporters. First, we have bile salts, transported by the BSEP pump. These salts provide the main osmotic drive to keep bile flowing and are essential for dissolving dietary fats. Next are phospholipids, specifically lecithin, secreted by MDR3. These form mixed micelles with the bile salts, acting as a buffer to protect our bile ducts from the harsh, detergent-like effects of the salts themselves. Finally, cholesterol, which is exported by the ABCG5 and ABCG8 transporters. Maintaining the exact right balance between bile salts and cholesterol is critical. If that balance tips, cholesterol can precipitate, leading to gallstones. On this slide, I've provided a reference table detailing the major hepatobiliary transporters, their locations, and their functions. While we won't read through every row right now, notice the right-hand column. You can see how specific genetic defects in these transporters map directly to well-known clinical disorders, from Rotor syndrome, involving the OATP transporter, to various types of progressive familial intrahepatic cholestasis, or PFIC, involving BSEP, MDR3, and FIC1. Stepping back to look at the big picture, the healthy human liver secretes roughly 1 to 2 liters of bile every single day. It is a complex, watery solution containing electrolytes, bile acids, cholesterol, phospholipids, and of course, the bilirubin pigments we discussed earlier. Ultimately, bile has 2 primary jobs: emulsifying and absorbing the fats we eat, and acting as the vehicle to excrete metabolic wastes. Our final stop is the intestines. Once bile empties into the gut, intestinal bacteria get to work on the bilirubin, reducing it to urobilinogen and stercobilinogen. From here, a highly efficient recycling program kicks in, the enterohepatic circulation. About 95% of the bile salts are reabsorbed in the terminal ileum and sent right back to the liver to be used again. As for the remaining waste, the stercobilinogen is oxidized into stercobilin, which is exactly what gives feces its characteristic brown color. Meanwhile, a small fraction of urobilinogen makes its way into the systemic blood, travels to the kidneys, and is excreted as urobilin, giving urine its yellow color. From the destruction of a red blood cell to the precise molecular pumps of the liver, the story of bilirubin in bile is a masterclass in human physiology. Thank you so much for your time and attention today. I would now like to open the floor to any questions you might have regarding bilirubin metabolism, transporter defects, or biliary dynamics.